Today we're going to be taking on the citrate shuttle system. So we're taking on the citrate shuttle system. So the citrate shuttle system is all about how it's all about transporting acetyl CoA from the mitochondria into the cytoplasm of the cell. So remember that beta oxidation actually occur in where the mitochondrial matrix, and pyruvate dehydrogenase actually act on pyruvate to convert it to acetyl CoA in the mitochondria. So that means acetyl CoA is mainly produced inside the mitochondria. We get um, high amount of acetyl CoA is present in the mitochondria. So for us to actually synthesize, when there is high amount of nutrient, when there's high amount of nutrient in the body, like when there's high amount of glucose, high amount of triglyceride, you understand? So we have to actually, sorry, let me change the pen. We have to actually transport acetyl CoA here into the cytoplasm for us to be able to synthesize. Because when there's high amount of energy, which hormone is actually secreted? Insulin. So it's insulin that is secreted when there's high amount of nutrient available, so that we can store some glucose in form of glycogen, and now we're going to be synthesizing fatty acids so that we can store them instead of using them, because the amount of energy, there's availability of these nutrients now. So there's no shortage yet, so we have to store these ones. So, and the major organ that is actually uh, involved in this, that actually synthesize high amount of this fatty acid, is the liver. So we assume that all this, from this fatty acid shuttle system to the pathway, to when I finish the pathway, we assume that we are in the liver. So maybe we just pick one of the liver cell and we're actually doing this. Adipose tissue too synthesize too. Yes, adipose tissue synthesize fatty acid too. But the major organ that perform the function is this liver. But adipose tissue mostly deal with storage, but it also synthesizes fatty acid. So it stores triglycerides. So that's fatty acid that's esterified with glycerol. So now we're going to take on how this pathway, how this citrate shuttle actually works. So some of the enzymes involved in this citrate shuttle, some of them are uh, part of the enzymes that actually catalyze some steps of the Krebs cycle. So like you can see here, you can see citrate synthase is part of the citrate shuttle. Sorry, part of the Krebs cycle. The first step is even the first step. The first step is one that catalyzes the first step of Krebs cycle. But this citrate lyase is not part of Krebs cycle. Some of the enzymes are part of the Krebs cycle, some are not. So now we'll see the action of this citrate synthase. So the action of this citrate synthase involves some nucleophilic reaction. So we just talk about how this citrate synthase actually performing its function. So we're going to talk about the neutrophilic reaction because that's a very big topic on its own. So now, as you can see here, we have this acetyl CoA here. So for us to actually perform this function now, we remove this acetyl group. So remove this acetyl group here. So you now have CH3 CO, you have minus. Then you have SCOA, the CoA will have minus. So now that means they are looking for one because I break the single bond in between them. So they're looking for, both of them are looking for one. So now this oxygen here bonded with this carbon with two electron. They both contributed to electron to form this double bond. So this ketone group is needing one. So if I give, with this oxygen attack this ketone group, now you have one free space here. You have two free electron at this carbon. Then this oxygen is minus because you can see it's supposed to be a complete COOH, right? But at physiological pH, they exist as carboxylate ion. So that's how carboxylic acid exists. But in some cases, they exist as like this. So sometimes when it's necessary, I'll represent it as this, or sometimes this. So I can be switching between the two. So now, what's going to happen here is that since we're having two electrons left here, so this CH3 now, for it to be able to have a free space so that it can bind, so that it can bind to this carbon, it will lose one hydrogen, and the hydrogen will be given to this coenzyme A here, and you have this. So that's why you see CH2 here. So now there's still one free electron at this carbon, with this carbon here. So this enzyme, citrate synthase, I told you there's some nucleophilic reaction involved in this. So it will add COH. So if it add OH, the OH will take the electron of this carbon. You get it? So the OH will take the electron of this carbon. The OH will take the electron of this carbon. So as you can see, you see that this structure is still available from here to here. You can see it here. Just that there's an OH added to this carbon here. So now this one, remember that this oxygen got attached to this. So you see it here, and this CH, it donated one electron to the CoA, and it gave coenzyme A, then to the coenzyme A, and you have this. So now this step is actually irreversible step. It's an irreversible step. So, but there's an enzyme that circumvent this step. So the enzyme is called ATP citrate lyase. So it uses ATP, it utilizes ATP. So it adds coenzyme A. When it adds coenzyme A, gives it to this, you get the coenzyme A will be given to this structure here, and you will get acetyl CoA. The coenzyme A will release the hydrogen, give the hydrogen to this CH2, it becomes CH3. Then the rest of the coenzyme A bind to this ketone group, leaving this oxygen here. So if it leaves the oxygen here, then this OH will be removed, and the oxygen will form a double bond again with this carbon, and you have oxaloacetate and acetyl CoA. And this is how this enzyme is found. This ATP citrate lyase is found in the cytoplasm of the cell. That's where you find this enzyme. This enzyme is present in the cytoplasm of the cell. So since it's in the cytoplasm of the cell, that means whenever the citrate enters through the citrate transporter to the cytoplasm, that's when this enzyme acts. So it acts to release the acetyl CoA. This acetyl CoA will now be channeled into synthesis. So see that. For now, let's go to the next step. So the next step here involves malate dehydrogenase 1 and malate dehydrogenase 2. Malate dehydrogenase 1 is an enzyme that is present in the cytoplasm of the cell. If you want to remember, if you enter a cell, you enter the cytoplasm first before you meet the mitochondria. So cytoplasm 1, mitochondria 2. So malate dehydrogenase 2 is found where? Mitochondria. So now let's see how they actually perform their actions. So, and this malate dehydrogenase 2 is actually the enzyme that is involved in Krebs cycle that converts L-malate to oxaloacetate. So this one is in the cytoplasm. So it's not part of the Krebs cycle enzyme. So is this malate dehydrogenase 2 that is part of the Krebs cycle enzyme. So now the oxaloacetate, this malate dehydrogenase 1 acts on oxaloacetate by what? Removing hydrogens. Sorry, adding hydrogen. Sorry, it adds hydrogen. You can see NADH. This is NADH. It adds hydrogens to it. So when it add hydrogen, let's see, we add hydrogen here, and we add hydrogen here. What do you think you have? You have an OH, because this oxygen initially was serving electron, and let's say, remember, two electrons, they combine it and form double bond. I'm just cutting from here. Sorry, let me clean this. I'm just cutting from here, the whole of this alone. Oh god, why is this not working? Okay, let me use red. I'm just cutting from here, the whole of this. So as you can see now, so if the hydrogen comes, it will bind to this electron. So this remaining electron will bind into this, still it will still remain bounded to this electron here of the carbon. So this carbon will be bounded to who? A hydrogen, an extra hydrogen too. So it's complete. You can see it bounded to hydrogen and OH. So you have your L malate. So you have L malate. So while this malate dehydrogenase 2 reverse this reaction, what does it do? It removes this hydrogen and this hydrogen, bringing it back to this step, to this oxaloacetate. Bring it back to this oxaloacetate. So we move to the next step. We have to be fast. So malic enzyme. So I'm showing you all these steps so that when I start the transport, you actually know what's actually happening. If I mention the enzyme, you get to understand, oh, this is what the enzyme did. This is the enzyme performing its function. So this is the action of the enzyme. So you get to understand how everything is moving. So you get to understand what's happening. So that's why I'm doing all this. I'm so sorry if I'm taking your time. So this malic enzyme. So malic enzyme is NADPH dependent, not NADPH dependent. So now, this malic enzyme, what it does is it will remove carbon dioxide. So from who? From malate. So it remove carbon dioxide from malate. Convert malate to pyruvate. So it removes carbon dioxide from malate. Then it removes hydrogens too. Hydrogens. So you see, it removes carbon dioxide and hydrogens. So if you remove them, what do you think you have? You have C double bond O, CH, 2, COO, right? That's how it's supposed to be, right? But look at it. This is how it's supposed to be. This is how the structure is supposed to be. Not like this. So that's how you think it's supposed to be. So now this is exactly how the structure is supposed to be. You have COO minus, then COH, double bond CH2. So this is the enol form of pyruvate. Enol form. So this is what we'll have when this happens. You get it? This is what we're going to have. This is how the structure is going to be when it happens. So I told you that some of these enzymes, what they do is they add to compound. They add how like it? They add more electron. They can just add an electron, extra electron, to actually get the structure they want. So now, as you can see here, we had this, and we had this, but an extra electron is coming from somewhere. So it's a work of who? The enzyme. So when this happens, when you have the enol form, the enol form spontaneously can become the what? Keto form. So the keto form is this. So spontaneously it become like this. So this hydrogen will be given to this, become CH3, and this will create a double bond. This double bond will not be here again to be a single bond, to create a double bond. So you have a pyruvate structure of pyruvate. So let's move fast. We have to run. So I think I have something to say. What do I want to say? Okay, that's it. So the next enzyme here is pyruvate carboxylase. It sounds like acetyl carboxylase. They perform similar kind of reaction, but they're not the same. They're not the same. They're not the same enzyme. So pyruvate carboxylase, what it does, it add oxygen, carbon dioxide to pyruvate. It's added here in exchange for hydrogen. So hydrogen is removed. One hydrogen is removed to create space, to create an electron at this carbon, to create a free electron at this carbon, so that this can be attached. So you now have COO minus. On your norm, I told you it's supposed to be like COOH, but because of what, the physiological pH exists as this. But sometimes they can exist as this, but more in physiological pH is carboxylate ion. So right, this hydrogen cannot be added to it to become like this. So this hydrogen is removed and this will enter. This requires ATP. Remember, you can see now we have used 2 ATP to do this to actually perform this transport. For this transport to take place, we have used 2 ATP. So take note of that, please. We have used 2 ATP for this transport to take place. So now, so at the end of this video, I think I'll say something about that. So you can see now I want to tell you the sources where we actually can get acetic CoA from. We get it from beta oxidation, I said this earlier. We get it from pyruvate dehydrogenase, I said this earlier. So these are the sources. These are the major sources. Some you can actually get it from some amino acid too, but these are the major sources, the major sources where we get amino acids. Sorry, acetic CoA from. So these are the major ways we actually generate acetic CoA. These are the major way we generate acetic CoA. So we'll go to the steps now, proper. Yes. So let me draw mitochondrial membrane. Sorry, I need a transporter. It can't just be So this is the mitochondrial membrane, and these are the transporters. So now, imagine we started with citrate the other time. So this is citrate, and we are the mitochondria. So I remember I told you there are acetyl-CoAs in the mitochondria. So imagine this acetyl-CoA combined with oxaloacetate. It gives us citrate. So this citrate is transported through citrate transporter into where the cytoplasm. So when it enters the cytoplasm, what happens? So which enzyme will act? Remember, the enzyme that acts here is who? Citrate synthase. Citrate synthase. So that's the enzyme that catalyzes this step, citrate synthase. Then when it gets into the cytoplasm, who will catalyze the next step? It will be who? ATP citrate lyase. ATP citrate lyase. So ATP citrate lyase catalyze it, converting it to oxaloacetate and acetyl CoA. So we'll drop our CoA there. But for us to continue this step, for it to be like a cycle. So now this oxaloacetate that is formed is converted to malate by who? Malate 1. Remember I told you enter the cytoplasm first before you go to the mitochondria. So there is malate 1. Malate dehydrogenase 1, sorry. Malate dehydrogenase 1 is one that catalyzes this step. So you can see the reason why I try to show you guys how the structures were being arranged or being acted upon by those enzymes. So now, malate dehydrogenase 1 acts on oxaloacetate to give malate. So malate to be acted upon by who to actually give us pyruvate. Yes, do you guys remember who? Malic enzyme. So malic enzyme. So we give us pyruvate. So this malate can also be taken through malate transporter to be acted upon by which enzyme to give us oxaloacetate pyruvate carboxylase. So pyruvate carboxylase acts on it, and remember now it's in the mitochondria, so it acts on it, it's converted to oxaloacetate, and it can react with acetyl CoA again and give us citrate again. So this pyruvate can also be transported through this pyruvate transporter. So pyruvate will go, pyruvate will now be acted upon to generate oxaloacetate. Pyruvate will be acted upon by pyruvate dehydrogenase. Pyruvate carboxylase. Sorry, I need to clear something here. Pyruvate will be acted upon by pyruvate carboxylase, right? Then remember I told you guys that malate and the mitochondria, malate dehydrogenase 2 acts on malate to convert to oxaloacetate. So I mistakenly said pyruvate carboxylase. So when malate gets into the mitochondria, it is converted to oxaloacetate by malate dehydrogenase. Then the pyruvate, when it gets into the mitochondria, it's converted to oxaloacetate by pyruvate carboxylase. Pyruvate carboxylase. I use PC to represent it. Here is malate dehydrogenase 2. Man, I'm making a lot of mistakes. So it's pyruvate malate dehydrogenase 2. Then here malate dehydrogenase 1. So you can see. So if you convert to oxaloacetate, it can go to citrate, go back, and you get it. You get your acetyl CoA. So now you will see that if you observe when I was showing you guys the structures, you observe that malic enzyme was NADPH dependent, and it generates carbon 4 oxide. So this NADPH is utilized. Remember, this malic enzyme is performing its action here at the cytoplasm. So this NADPH produced is actually going to be used in the synthesis pathway. The synthesis, because NADPH is involved in the synthesis. Then NADH is involved in degradative pathway. So this one is involved in synthetic pathway. This NADPH. So this carbon 4 oxide 2 is going to be used by acetyl CoA carboxylase. So as you can see here, and again, the major source of this NADPH is actually from pentose phosphate pathway. The major source is from pentose phosphate pathway. So that's the major place where we actually get this NADPH from. So if you can see here, remember we used 2 ATP. I told you the other time to actually generate. We used 2 ATP to actually generate what do you call it? To actually carry out this transport, right? So when this acetyl CoA is actually generated here, there's an enzyme called acetyl CoA carboxylase. That's the rate limiting enzyme of fatty acid synthesis. So that's the rate limiting enzyme of fatty acid synthesis. So it will act on this acetyl CoA. You will see it in the pathway when I start the pathway. So you see how this enzyme actually performs this function to act on it and convert to malonyl CoA, but it uses ATP. So now that means that for us to actually carry out the synthesis, this synthesis, one acetyl CoA, if you transport one acetyl CoA to the cytoplasm, the step is to actually start, which is the step that will be catalyzed by acetyl CoA carboxylase that uses 1 ATP combined with the transport. It will give us 3 ATP. That means 1 acetyl CoA will consume 3 ATP. So if let's say you are like you want to synthesize fatty acid now. Fatty acid, which the fatty acid you want to synthesize is let's say palmitic acid. You will need 8 acetyl CoAs. And in fatty acid synthesis, one acetyl CoA goes into the pathway directly, then the remaining ones are going to go indirectly as malonyl CoA. So let's say the one that goes directly is and the one that goes indirectly, those ones that go indirectly, they're going to be acted upon by who? They're going to be acted upon by acetyl CoA carboxylase. So that means 7. If it is palmitic acid we are synthesizing, remember I said you need 8 acetyl CoA. So one will go directly. So that one that will go directly, we only use 2 ATP since it will not be acted upon by acetyl CoA carboxylase. Then the remaining 7 we utilize 3 ATP, right? They utilize 3 ATP. So if you say like let's say 7 plus 7, you will have 14. Plus 7, you have 21. Then plus 2, you have 23. That means to actually synthesize uh, palmitic acid now, you use 23 ATPs. Yes, 23 ATPs. That's what you utilize. You utilize 23 ATP. So um, the actual what actually stimulates this enzyme here, the one I called acetyl CoA carboxylase, is citrate. When there's high amount of acetyl CoA, so as you can see, this increase in citrate ions actually stimulate this enzyme. So we'll talk about the regulation of this synthesis when we take on when I produce video on the regulation of fatty acid pathway. So we'll talk about how this enzyme is being regulated. So thanks for watching, and please subscribe and turn on the notification bell. Thank you. I'm sorry for the mistakes.